is Renfei Zhou from Carnegie Mellon University. He is an expert in theoretical computer science and is going to talk on new breakthrough in matrix multiplication for the next hour. Welcome.
Thank you. Thank you for the introduction. My name is Renfei, and today I'll talk about matrix multiplication algorithms. Oops, why this doesn't work? Oh, it works. It's just laggy. So this talk is based on our recent sequence of 3 papers from our research group. Although this is supposed to be the FSA lecture for the second paper here, but I will talk about all 3 of them because they are closely related to each other. Let's start by appreciating a comic about theoretical computer science. It says that mathematicians are very weird in that as long as a magical number around 2.373 gets slightly improved, then everyone gets super excited about it. This is because this magical constant is related to matrix multiplication, which is one of the most important questions in theoretical computer science, and people do care a lot about its computational complexity. And that's also the topic of our talk today. But before we start, let me mention that this talk is supposed to be interactive, so if you have any questions, you can just interrupt me and ask the question. Otherwise, the talk would be a little bit too short, so your questions are an important part of my talk. Let's start by introducing the matrix multiplication problem itself. In this problem, we want to multiply 2 matrices of n by n, and we want to compute the product. The mathematical definition of matrix multiplication is written here, although it is very well known, and I believe I don't have to repeat it again. But the question we are asking is the optimal number of arithmetic operations that we need to calculate this product. The answer to this question is still denoted by a single real number omega, which is called the matrix multiplication exponent. It means that we need n to the omega time to calculate this product. For this number omega, we know it is at most 3, because if we directly follow the mathematical definition to calculate the product, we will spend n cubed time. And we know omega is at least 2, because in order for us to read the input and print out the output matrix, it already takes n squared time. But between 2 and 3, it is a big open question in computer science to determine the best possible complexity. Although the most standard parameter regime cares about multiplying 2 square matrices, as we just see, there's also a closely related setting of multiplying rectangular matrices. Let's say if we want to multiply the first matrix of n to the a by n to the b, and the second matrix of n to the b by n to the c, then we will use this notation, omega of a and b and c, to represent the optimal exponent of multiplying matrices of those shapes. Here, a, b, and c are absolute constants that does not scale with n. And among all of the questions of this type, there's one special case that we care the most, which is shown on the picture here. We want to multiply the first matrix of size n by n to the alpha, and the second one of n to the alpha by n, and we wonder how large can alpha be if we want to multiply those 2 matrices in almost linear time. This largest possible alpha is called the dual matrix multiplication exponent. Again, for this constant, we only know that it is between 0 and 1, but its exact value remains a big open question. Many people in theoretical computer science believe that omega equals 2, which means that matrix multiplication problem itself can be solved in almost linear time. And an equivalent expression of this conjecture is to say alpha equals 1. So if we can improve the lower bound of alpha, proving better and better lower bounds, that's an alternative view of improving the complexity of matrix multiplication. So this is the definition of rectangular matrix multiplication. It's also important and widely studied and widely applied but it will not be the main focus of our talk today. It's because the techniques here are closely related to the techniques on the square matrix multiplication. So today we will be mainly talking about multiplying square matrices. That is the constant omega on the previous slide. So one reason people care a lot about matrix multiplication is because it has many applications. In theoretical computer science, the application mainly lies in two main categories. The first one is linear algebra. This is because it's been known that the computational complexity of multiplying matrices is equivalent to that of many other matrix operations, including computing the inverse of a matrix, computing the rank, the determinant, and many others. So if we can create faster algorithms to multiply matrices, that also allows us to do a lot of matrix operations, which can enable for a lot of things to do. The second category is in graph algorithms. This is because multiplying the adjacency matrices of graphs had a very clear combinatorial meaning of counting paths in a given graph. So that's why fast matrix multiplication algorithms has been widely used as crucial subroutines in many state-of-the-art graph algorithms. And besides those theoretical fields, there's also applications in, for example, machine learning, computer graphics, optimization, and scientific computing, those areas in computer science. This is largely because those fields of computer science tends to model their questions using the language of matrices, and therefore being able to multiply matrices becomes a basic need in those fields. So this is why people care a lot about matrix multiplication. Historically, people made a lot of effort trying to prove better and better upper bound omega, as listed in this table. At the bottom, you can see our recent sequence of works that obtained the state-of-the-art bounds up to 2.313 something. But you may notice that this table is a little bit hard to read. It's not very intuitive. So let me show you a picture instead. Not working? What? Okay. Okay, here's the picture. This is a curve that shows the best bound on omega as a function of the year. It starts at the top left corner with the trivial bound omega bounded by 3, which means that we can always multiply matrices according to the definition, which takes n cubed time. And there's been a large sequence of improvements in the middle that corresponds to the sudden drops in the bound. And it finishes with our recent best bound of 2.3713 something. And if you look at all of the improvements in the middle, you may notice that some of the improvements are significantly larger than others. Those are considered the revolutionary moments in this line of research. The first revolution was made by Strassen in 1969. He discovered the first subcubic algorithm for multiplying matrices and proved that omega is bounded by 2.8 something. And the second time was by Schoenhag in 1981. He further improved omega to 2.5 something. And the third time was by Coppersmith and Winograd. They improved omega to 2.37 something, which is already a little bit close to the best bound we know today. Like the current best bound shares the first two digits after the decimal point. And actually, those works are called revolutionary works, not only because they've made the largest changes in the number omega itself, but also because those works introduced impactful ideas to this field. For example, the first revolution comes with the idea of divide and conquer framework, which forms the absolute basis of all the algorithms from that time until today. And the second time introduced the asymptotic sum inequality, which is a generalization of the divide and conquer framework that allowed us to design the algorithm in a more flexible way. The third time was the introduction of Coppersmith-Winograd tensor and also a powerful tool called the laser method, which we'll mention a little bit later in this talk. These tools together form the modern framework of matrix multiplication algorithms, in that all of the subsequent improvements lies within the framework introduced by Copsmith and Winograd. So you can see that after the 90s, all of the improvements are relatively invisible compared to the three major revolutions along the way. So those are the three main revolutions. Sure.
So the worst case about the value omega, for example.
This is a very good question. So the question was, is there a known lower bounds for this question? The general answer is that we don't have unconditional lower bounds saying that we cannot achieve omega is 2. Like whether we can achieve omega is 2 or not still remains open. But there are some conditional lower bounds that actually proves the limitations of existing frameworks. For example, there's been known that if we still live in the framework introduced by Copsmith and Winograd, we can never break omega is less than 2.30. Like that's a conditional lower bound. So thank you for the question. Other questions? Then let's continue. So these are the three main revolutions. And if we take a closer look into the part from 1990s until today, although all of those improvements are relatively smaller compared to the three major ones, there are still some relatively larger improvements that brought important ideas into the field. The first one was made by Stothers and Vasilevska-Williams. They improved omega on the third digit after the decimal point until like 2.372 something. And they did this by introducing the computer-assisted proofs into this line of research, which means that in the paper, we only prove, like, for example, if we solve this optimization problem, then the answer to it could be a valid upper bound on omega, and then we write computer programs to actually calculate how large omega is. Starting from that moment, improving the upper bounds on omega is no longer purely a mathematical and intellectual game. It is also a computational challenge. And the final one was our recent sequence of works that introduced the combination loss analysis. We will mention a little bit later in the talk that this is to point out a hidden loss in the existing framework of Copsmith and Winograd that previous papers didn't realize. And once we realize this loss, we can design some ad hoc techniques to partially reduce this hidden loss, which allowed us to further change the third digit after the decimal point. And this curve is an overview of this line of research. Before we continue, any questions? Sure.
We're very interested in the computer-assisted proof. So sometimes we can use computer to have some result. So you see, if we see proof, for example, mathematical proof is all time correct, right? So what kind of level about this computer-assisted proof? It is something like mathematical proof. It must be true, or that's some numerical evidence.
It is always true. It is like the computer part is part of the mathematical part. It's just that it is too large to write down on a physical piece of paper. So theoretically, you can also copy down all of the data and inequalities to form a completely mathematical proof. It's just too large. This is a good question. So rigorously speaking, we also need to do like floating number error analysis to make sure it is completely correct. Although some papers like omitted this part historically. But theoretically, this is something we should do. Thank you. Other questions? Then let's continue. In the rest of the talk, I will first tell you a little bit about how the modern algorithms of matrix multiplication works so that you can feel where does the recent improvement arise. Let's start by introducing tensors. Tensors are very common mathematical objects, and there are a lot of equivalent ways to define tensors. To let our talk be less technical, we will say that tensors define the structure of bilinear problems. This picture shows an example of bilinear problem. We have two sequences of input variables, xi and yj, and we want to compute a sequence of output variables based on the input. How to compute is defined by the tensor structure on the left-hand side. It is a formal summation over various terms where every term describes a single step in the calculation. In each step, we want to take the input variables xi and yj, multiply them together with a leading coefficient aijk, and add the result onto the kth output position. After we complete all of those steps, the sequence of output variables we get is defined to be the answer to this bilinear problem. So you can see that the tensor and the bilinear problem has a one-to-one correspondence with each other. Matrix multiplication is also a special type of bilinear problem, so we have a special class of tensors to describe their structures. These are called the matrix multiplication tensors and written in this notation, n, m, p within angle bracket, and we say this is a matrix multiplication tensor of size n by p. What it means is that in this underlying bilinear problem, we want to multiply the first matrix of n by m and the second one of n by p. So if you read the formal summation here, read the mathematical definition, then every term within the summation will correspond to a single scalar multiplication that we want to do if we follow the mathematical definition to calculate this product. But if you read the research papers in our field, you may realize that this is not how people define matrix multiplication tensors. People conventionally will transpose the output matrix C to let every term read like aij times bjk times cky, so that there's a rotational symmetry between all three dimensions and all three indexes here. From here, you can already see the first benefit of using the language of tensors. That is, it establishes a symmetry between input and output dimensions. We already said that tensors can describe the structures of bilinear problems. And in this talk, we will also take an alternative view of tensors. That is, we view tensors as computational resources that actually help us calculate the product. The underlying bilinear problem. For example, if I say that we have a matrix multiplication tensor of n by p in our hand, what I mean is that we can actually use this resource to calculate the product of two matrices of given sizes. This alternative view of tensors will help us understand better the relationship between different tensors and different problems. An important quantity about a tensor is its rank. The rank tensor is defined by writing down the tensors as a summation of as few terms as possible of the so-called rank 1 tensors. Each rank 1 tensor is just a linear combination of x variables times that of y variables times that of z variables. So the minimum number of terms we need to write t in this form is defined to be the rank of t. This definition is very similar to matrix rank, which we are all familiar with. The only difference is that matrix is a two-dimensional object, so there will only be two factors within each term in the summation. But in this talk, we are caring about three-dimensional tensors, so here are three factors instead. The rank is used to measure the algebraic complexity of a tensor. So if the rank is higher, we say the tensor is more complex. And this notion of rank is closely related to our mission of proving upper bounds on omega, because we have this theorem. If we can show that the rank of a matrix multiplication tensor of size m by m is bounded by integer r, then that immediately leads to an upper bound on omega that equals the logarithm of r in base m. How I personally understand this theorem is as follows. We already know that tensors describe the bilinear problems, and we view them as computational resources. And rank of the tensor corresponds to the price of this type of resource, which means that when the rank is higher, it is more difficult to obtain this tensor as computational resource. In this intuitive language, what this theorem on the top is saying is that if the matrix multiplication tensor of a given size is relatively cheap, then we can use limited cost to buy a lot of such tensors, which would be extremely helpful for our mission of multiplying large matrices, and that leads to an upper bound on the complexity of multiplying matrices. So this is how we're going to use the rank of tensors. Next, let's move on to introduce the Coppersmith-Winograd framework. It is the basis of all of the algorithms from 1990s until today. The high-level picture of the Coppersmith-Winograd framework is shown in this picture. We want to find a type of a resource, which is usually described using the language of tensors, and we hope it to satisfy two nice properties. The first one is that the resource should be relatively cheap, which means that the tensor should have a small rank. And the second property is that the tensor should be somehow useful for our goal of multiplying this. As long as those two properties are true, we can use standard techniques to argue that the computational complexity for matrix multiplication must be bounded by something. So this is the high-level picture. So in the Coppersmith-Winograd framework, what they usually do is to take the so-called Coppersmith-Winograd tensor. For this talk, we are not spelling out the mathematical definition of the Coppersmith-Winograd tensor. Just keep in mind it is some basic mathematical object that had some nice properties. That's enough for this talk. And we take the tensor, we raise it up to a high tensor power, which forms a huge tensor, and we write it on the left-hand side. This huge tensor represents a large bilinear problem, and a nice feature of Coppersmith-Winograd tensor is that this problem is cheap to compute. It's easy to argue that. Can you say it again? Valency? Sorry, I didn't understand. Balance? Sorry, maybe. Oh, you mean 3-dimension? Okay. Coppersmith-Winograd tensor is also a 3-dimensional tensor. Space. It depends on some hidden parameter that I didn't spell out in the Coppersmith-Winograd tensor. For now, you can assume it is a constant. I think maybe I'm misunderstanding you. I feel like I'm misunderstanding part of your question. Can we discuss this afterwards? Thank you. So let's go back to this. So we were saying that by taking a high power of the Coppersmith-Winograd tensor, we get a large, we get a large bilinear problem, which we write on the left-hand side, and we know it is cheap to compute. Then the second step in this framework is to perform a complicated process called the laser method, which degenerates the tensor on the left-hand side into the right-hand side, which is a large collection of matrix multiplication tensors. You can think of this degeneration as a reduction from the right to left, which says that as long as we can compute the problem on the left-hand side, then we can use exactly the same resource to compute the problem on the right-hand side, which means that we can use that resource to multiply a lot of matrices. And this reduction is a explanation of the Coppersmith-Winograd tensor being valuable for our task of multiplying matrices. So that property combined with the earlier thing that the left-hand side is cheap to compute would give us a upper bound on omega using standard technique. So this is how Coppersmith window graph framework works. And in fact, in this entire framework, the only step that we can hope to improve is the degeneration in the middle. And all other steps are already optimal and fixed in the framework. If we can somehow come up with a better degeneration in the middle, that means that we can take the same input tensor on the left-hand side, but produce larger and more multiplication tensors on the right, which will intuitively give us better bounds on omega. And in fact, improving this laser method in the middle was how people made all of the improvements after the seminal work in the 1990s. For this talk, like the way we understand degeneration is that it is a reduction, saying that if we want to solve the problem on the right, then it suffices to solve the problem on the left. And degeneration, you can think of it as a like this sentence translated to the mathematical language that works closer to tensors, but it describes the same thing. Oh, so once you get those, you then substitute this into the earlier framework obtained by Strassen and other people, and there is a standard framework to transform this into an algorithm with specific time complexities. But I'm not going to dive into the details about that part. Correct. Other questions? So this is how Coppersmith window graph framework works. And now let's see a picture showing how the degeneration works. This picture is different versions of the laser method used in historical papers. The left column is the one used in some historical papers before our recent works. The middle one is used in our 23 paper, and the right column is in our 24 paper. We try to integrate new ideas and techniques to improve the performance of the degeneration, and once the degeneration is improved, recall that we can get better bounds on omega automatically. But you may also notice that those processes are rather complicated. They contain a lot of steps, and each step here is actually representing a larger sequence of sub-steps on the algorithms, which makes it totally impossible to teach you how laser method works within an hour. So what I will do instead is to show you a toy example that illustrates our high-level idea behind the recent improvement. But before we get into the toy example, is there any questions about this part? Okay, let's move on. So next, I'm going to tell you a toy game that illustrates the difference between our method and traditional laser method. It's a little bit laggy, sorry. So in this toy game, we have a universe of n elements. They represent some type of resource. And there's also a sequence of sets, A, B, C, and so on. Each set contains n to the 0.99 random elements in the universe. And for each set in this sequence, let's say A, if we would like to consume all of the elements in A, that will give us a matrix multiplication tensor of size n by n by n, which is a valuable resource that we really want. The same opportunity applies to all of the sets B, C, etc. in the sequence, but the tricky thing is that every element in the universe can only be consumed once. Under these constraints, the goal of this toy game is to obtain as many matrix multiplication tensors as possible. For now, let's first look at two of the sets, A and B, instead of a lot of sets. Because both A and B are large and random sets in the universe, with high probability, they will share a small intersection part in the middle. Which means that if we want to consume all of the elements in A, we will not be able to do that again for B because they share some elements, but every element can only be used once. So in this situation, the traditional laser method just says that let's simply utilize a single set A and discard the other one. So we get one matrix multiplication tensor in the end. But in our recent work, in our 23 paper, we introduced a new approach. We start by manually deleting the intersection part in the middle, like shown in this picture. This will transform both sets A and B into the so-called broken sets, which means that a fraction of the elements in both sets are missing. But the good thing is that the two broken sets are now disjoint from each other, so we can utilize them separately. The hope of our new approach is that if a broken set can still give us something meaningful, then we can take advantage of the increased number of sets that we have. So the question becomes, what can a broken set give us? We already know that a normal set can give us a matrix multiplication tensor. And if we dive into the technical context of this toy game when it shows up in the laser method, we will also be able to show that a broken set can give us a broken matrix multiplication tensor. This tensor can still help us multiply two n-by-n matrices, but in the output matrix, we can only get the answers to some of the entries, but not all of them. The other entries, which are shown in black here, they are the holes of this, they're called the holes, and we cannot get answers to those locations because the tensor is broken. You can view this broken tensor as one obtained from a normal tensor by digging holes in the output dimension. And this type of tensor was first studied by Schoenhack in his seminal work in 1981, but he was using this type of broken tensors for a completely different purpose than us. So this broken tensor is what a broken set can give us. Surprisingly, broken tensors and unbroken ones are just almost equivalently powerful with each other. Let's suppose that we have order and log n copies of a broken matrix multiplication tensor, and in each tensor, a random half of the output entries become holes, so we cannot get the answers. And suppose that we want to use those tensors to multiply to n-by-n matrices. Here's what we can do. We first take the two matrices that we want to multiply and feed them into all of the broken tensors we have, so they all get the same input. Then, each broken tensor will reveal to us a random half of the entries in the output matrix. In the output matrix that we want to compute, for every entry, we only need it to be revealed by one of the broken tensors so that we know the answer at that location in the end. And because we have n square entries, and we have order and log n broken matrix multiplication tensors, with high probability, every entry will finally be revealed by at least one tensor. So what we get in this process is the entire output matrix without any holes in it. This means that order and log n broken matrix multiplication tensors can actually help us calculate to multiply to n-by-n matrices and get the entire output matrix, so they are equally useful as a single unbroken tensor. In this sense, broken and unbroken tensors are just equivalent to each other up to a factor of log n in the number of tensors we have. So this is the technique of fixing holes. Now, let's move on to introduce our new approach in the 23 paper. We start by taking n to the point 0,1 many sets instead of only 2 sets. And then in the second step, we manually delete the intersection part between every pair of sets, which means that as long as an element appears in 2 of the sets, it got removed in the second step. This will transform every set into a broken set, where a constant fraction of elements are missing. And finally, we perform the technique of fixing holes to transform those broken tensors back into unbroken ones. The final step will cause us to lose a factor of log n in the number of tensors we have, but that is just negligible compared to the polynomial gain in the numerator. So in the end, what we will get is a large number of unbroken matrix multiplication tensors, which are much better than the one matrix multiplication tensor in the traditional approach. One question in this new approach is why we cannot start the algorithm with more chosen sets so that we get more tensors in the end. The answer is related to the size of a single set compared to the entire universe. We use the letter P to denote the ratio between the size of a single set compared to the entire universe. And in our parameter setting, P will equal to n to the minus 0.01. Once P is given, the correct number of sets we need to choose is P inverse. And under this parameter, if we multiply the size of a single set and the number of sets we choose, that already approaches the level of the entire universe size, which means that we are basically utilizing every element in the universe very well. If we further increase the number of sets we choose, we cannot utilize more elements because there are no more elements to utilize. But instead, we will make the intersection part between sets larger and larger, which can only be harmful for our algorithm here. That's why we should always choose 1 over P to be the number of sets. And when we follow the calculation, we will get P inverse broken tensors approximately. You can see that if we start the toy game with a smaller parameter P, then this will give us a better improvement than the traditional approach. This is intuitive because a smaller P is not for free. A smaller P means that we can start with a smaller set of elements, which represent resource, but still being able to produce the same powerful outcome of n by n by n. And that is a stronger condition that intuitively provides better bounds on omega. And improving the parameter P will be the focus of our subsequent work in 24. But before we, wait, I pressed the wrong button. Before we move on to introduce the subsequent works, let's first use this picture to summarize everything about the toy game. In the traditional approach of the toy game, we just take a single set, which directly gives us a single tensor. But in the new approach in our papers, we take a large number of broken sets, transform them into broken tensors, and finally perform the whole fixing technique to get many tensors, P inverse tensors in the end, which is much better than the one tensor on the left-hand side. And this difference between one tensor and P inverse tensors is what we call the combination loss, or the hidden loss in previous work. And after introducing the combination loss analysis, we wrote 2 other papers to further refine and improve the techniques here from 2 different perspectives. The first one in 2024 aims to prove a better starting condition on the parameter P. And as we said, if we start the toy game with a smaller parameter P, we will get a better bound on omega automatically. Let's go back to this flowchart on laser methods again. The middle column is the process that we use in our 23 paper. There are some distributions in this complicated process that have something to do with the parameter P in the toy game. And we designed some ad hoc steps in blue boxes to deal with those distributions. But later on, we realized that those steps were not utilizing very well the full power of the distributions. So we decided to combine them into a simple combined step, which provides better parameters of P. And that would imply a better bound on omega. At this point, we thought that this would be an easy project to do, because all we need to do is to change 2 of the steps in such a large algorithm, and all other steps just remain the same as the previous work. And hopefully, the analysis can also carry over, and all we need to do is to analyze this modified step. But it turned out that we were all wrong, that combining those steps into the new step will create a lot of challenges that we need to overcome. We started with the new definitions and new ways to deal with the distributions, which are the reason why we get better bounds on the parameter P. But those modifications in the algorithm creates additional issues. First of all, the number of holes in our algorithm after the modification becomes much more than the previous works, so that we cannot afford. Also, the holes begin to appear in all 3 dimensions simultaneously instead of only in the output dimension. To address these issues, we designed ad hoc techniques to reduce the number of holes in our algorithm and also to fix holes in all 3 dimensions simultaneously when the number of holes is under control. But those fixes again made hacky changes back into the definitions, which made every other step in this algorithm much more complicated. And finally, remember that all of the recent bounds on omega were computer assisted, so we needed to write computer programs to calculate the bound. And because our algorithm and analysis were much more complicated than previous papers, the computation becomes a real challenge. We had to write 4,000 lines of MATLAB code and ran the code for several weeks in order to calculate what omega is. It is very rare that in a theoretical computer science project, you can see this amount of coding, right? But after all of those challenges are resolved, we finally can make another significant improvement to omega. So this is an overview of what we did in our 24 paper. And in our 25 paper, we improved the techniques from a different perspective. We tried to play the toy game twice instead of once. This picture shows the sequence of sub-steps within a single stage of the laser method. The left column corresponds to the version we used in the 24 paper before our most recent improvement, and the right column is the new algorithm. In these sub-steps, there are some of them corresponds to playing the toy game on z dimension. This toy game will give us a parameter p, and because we are getting p inverse tensors instead of one tensor, this creates an advantage over the traditional approach. And why we only play the toy game once on one dimension instead of on all 3 dimensions simultaneously, this is related to how this toy game integrates into this technical context. Technically speaking, the toy game on z dimension requires some uniqueness conditions on the other 2 dimensions, x and y, which means that if we are going to play the game on z, then we cannot play the game on x and y in other steps of the algorithm. So that's why we are only playing it once. But in the new approach, we are doing something slightly different. We first play a partial version of the toy game, which gives parameter p of y. When I say partial, I mean that this toy game only relies on the uniqueness properties on x variables on x dimension, which means that we cannot play the game on x. But this game does not care whether we play the toy game on z or not play there. So that's what partial means. You can see that it is taking as input a weaker constraint on the uniqueness properties. And that's why the outcome p of y obtained by this partial game is also weaker than a usual game. After playing the partial game on y, we immediately perform some cleanup process to establish the uniqueness properties on the y dimension. So later on, when we play the second game on z dimension, it just cannot see that the game on y had ever happened. All it knows is that the uniqueness properties on x and y are already established, so the game on z can start as usual. The full version of the toy game on z is exactly the same as the one in the previous paper, so they produce the same advantage, but the partial toy game on y creates more but additional advantage, and this is the key point of making the improvement on omega again. So this is what we did in the 25 paper. So finally, let's summarize. We introduced the combination loss analysis, which means that in the toy game we introduced in the second part of the talk, we're getting p-inverse tensors instead of one tensor. And this technique, combined with the two subsequent refinements, together allowed us to improve omega from 2.3728 to 2.3713. It's improving the third digit. And although this talk has been talking about square matrix multiplication, our technique also generalizes to rectangular matrix multiplication, which allowed us to improve the dual matrix multiplication exponent, alpha, from 0.31 to 0.32, changing the second digit. We also made improvements to an important constant in graph algorithms, and as well as computational complexities for multiplying rectangular matrices of other shapes. And we included such a table in our paper that shows all of the bounds that we get. And that's all I want to share today. Thank you.
Thanks for the speaker. Now the question time.
Can you elaborate on how you actually use those matrix multiplication tensors that you produce with the laser method?
You mean produced by the laser method?
Yeah, like how do you actually use your algorithm to do a matrix multiplication?
This is a good question. Let me try to answer that briefly. So imagine that like after you use laser method to obtain a lot of matrix multiplication tensors, what you actually get is something similar to a rank bound on matrix multiplication tensors. This rank bound comes from two facts. One fact is that the starting tensor from the laser method is cheap. The second fact is that the the matrix multiplication tensor reduces back to the starting tensor that we are doing. So this together gives a rank bound on matrix multiplication tensors. And once you have a rank bound, that rank decomposition can form a suggestion on how you perform a divide and conquer framework to partition your large matrices into some smaller problems and do some linear combination of the subproblems to form a recursive algorithm. I know maybe this is a little bit vague. If you're interested, we can talk more offline. Thank you for the question.
Other questions?
So how many lines is your code overall?
Overall, I think it's 4,000.
4,000. Oh, okay. Thank you.
Your techniques extend to bounding the rank of other tensors besides matrix multiplication?
This is a good question. So in principle, our technique generalizes to any tensors that use a similar framework of laser methods. But so far, I think the main application of laser method is to bound the matrix multiplication tensors. But I know there are some other similar applications where laser method can also be useful, but those problems are like less studied than matrix multiplication.
Thanks.
Thank you.
So given that this framework has a lower bound you mentioned before, like 2.30, do you think that there will be a new framework to break this lower bound?
This is a very good question. I personally think the current framework might not be the ultimate answer to the matrix multiplication problem, and there are many people trying to find a new framework that is totally different to further push the computational complexity, but so far they haven't succeeded yet.
Can this method be generalized to other fields, say finite fields or fields with characteristic
This is a very good question. I think due to the Corpus-Winograd tensor, it cannot be generalized to any field. For example, maybe F2 is a little bit hard. But for large finite fields, I mean larger than a constant, like larger than 10, then this can generalize. Other questions?
If no more questions, let's thank the speaker again.
Thank you.